So what we're going to check out this video is looking at 3 different methods for how we can quantify the concentration or amount of an unknown within a solution that we've created. And for this analyte that we're going to look at, there's 3 methods we're going to look at, possible reasons why we choose one over the other. And those 3 methods are external standards, standard addition, and internal standards. And we're going to go ahead and talk through the 3 different types of these, as well as kind of the ways of why we would use them, when we would use them, and how we would use them, and the kind of pros and cons that goes with each of these. So let's first talk about our initial one here, which is the external standards, which is what we're probably more classically used to using within a chemistry context or biological context, or kind of any kind of analysis that is typically used for kind of wet lab, and that would be our external standards. So our external standard is one in where we take a solution and we're going to create a bunch of solutions that have a known amount to create a calibration curve. So we're going to go ahead and create like solution 1, solution 2, solution 3, solution 4, etc. And we're going to go ahead and make each of these with specific concentrations here that we would see. Those 4 different solutions that we may create, we're also going to have a blank that has no concentration in it. That's just kind of our standard like blank solution that has whatever the matrix is that contains our analyte. And then we'll go ahead and create a calibration curve. So we'll take those and we'll create a calibration curve where we have our concentration. And then we go ahead and take our signal. And then whatever that signal is, it could be an absorbance, it could be an emission value, it could be fluorescence, it could be the area when we're looking at maybe a chromatogram. There's all different kinds of signals that we could get when we're looking at these here. And I'm going to use S for our signal and C as our concentration. We will then go ahead and kind of plot these different solutions, and we will get a linear regression line from those. We then can use that in various ways. We can use the slope, we can use the y-intercept if it's a specific thing that we're looking at, but we're going to go ahead and utilize that. So we make specific solutions that don't contain our sample, right? We're looking at an analyte, we make these external solutions that don't contain our sample, and then we would go ahead and collect a calibration curve. Our next one would be kind of a standard addition. With our standard addition, we're going to add known quantities of our analyte to the unknown solution. So I'm going to go ahead and I'll start with kind of our unknown solution. And we'll go ahead and we have a specific amount of it. And then we'll go ahead and collect some kind of signal that we're going to get. We're going to call that signal supplied by X, our analyte. Then what we're going to do is we're going to take that and we're going to add a known amount of X to that solution. So we're going to add this standard. The standard that we're adding is a known amount of the analyte that we're looking at here. And that's going to give us a new solution that is going to contain the concentration of X is going to be from our unknown plus our standard. So we have a standard known amount and we have an unknown amount. And then we're going to go ahead, once we do that, again, collect another signal, whatever that would be, area, whatever we're looking at. And now the total signal is going to be the signal from X and the signal from our standard that we went ahead and added into that. And so we see an increase in absorbance or fluorescence or area, whatever it would be, for that signal by the added amount. And that's going to give us the ability to quantify how much of the unknown we have. The third one here we're going to look at is an internal standard. Now an internal standard is we're going to go ahead and we're going to add a known amount of a different compound than our analyte X. And we're going to add that to the unknown. So we're going to have first make kind of our standard solution that we're going to have. And here it's going to have X and Y. And so X is our analyte, Y is the kind of known, the other thing that we want to compare it to. It's a different compound. We want it to be maybe similar to it. If we're looking at chromatograms, we want to make it so that it has a maybe not overlapping, but similar retention time that we'd see there. But now this standard contains a known concentration of X, our analyte, and Y, kind of our internal, into the solution internal standard. Now this is different than a standard addition. Standard addition is we add the same thing. Our internal standards, we're adding a different analyte. And so now that we have a known amount of X and Y, we're going to get a signal for X and we're going to get a signal for Y. Now that's going to give us the ability to relate those to each other when we go ahead and collect another sample. So then now what we're going to do is we're going to have our actual unknown sample, and we'll take our unknown sample, again is going to contain X and Y. Now the difference here is that this contains a known concentration of Y, but an unknown concentration of X, our analyte. So the analyte, we don't know how much of it we have, that's what we're trying to identify, but we added this other sample, this other substance into that solution that we don't know the concentration of our analyte in. And that's going to again give us I'm going to call this signal prime for X and another signal for Y. And we're going to use that information to go ahead and quantify the concentrations that we would have. Let's go ahead and talk through how we're going to do that. So for when we're going to quantify our external standards, again, we typically just go ahead and take our concentration, and then we typically have our signal. Now this signal, there's one of two ways. We can subtract a blank, or we can leave a blank, and we'll see that that's going to take into consideration kind of that signal that we get just from a blank. Typically, this is going to be the signal of our standard minus the signal of the blank that we would get there. So we're going to subtract that. Then that should go through our 0 point. It should be something linear. And again, we're typically going to use a linear regression to find maybe something about our slope. And that's going to tell us something about how our signal relates to the concentration. Now, if we go ahead and replace our signal and our concentrations, we see basically our signal now becomes our slope times our concentration plus whatever our y-intercept is. Because our y values are signals and our x values are concentrations. And that gives us the ability to have a known relationship between our signal, again, absorbance, fluorescence, area, whatever it be, and our concentration of the analyte that we're looking at. Now we go ahead and we look at our second possibility. What we're doing is we're looking at an enhanced signal of our analyte by the addition of a known amount. And so what we're going to do is we're going to look at the ratio of signal 1, which is our unknown solution, and then we would have signal 2, which is going to be the total signal that we'd have with the addition of the known amount. And so we're going to see an enhanced amount that we'd see here. So our signal 1 is our unknown solution. Our signal 2, signal, whatever we would have, again, area, absorbance, whatever it would be. Our signal 2 is going to be, what we'd see here is the standard addition signal. So our solution that contains the known amount of what we added into it. And then what we're going to do is we're going to say those are, as long as our signals and concentration are proportional, which is they should be, which we're looking at these, we're going to say that that's going to be equal to basically the concentration, the ratio of our concentrations that we'd see here. Now what we're going to take into consideration is a dilution that would happen. Typically we don't just take the unknown solution, we typically dilute it to try and make them more similar when we're looking at this. So we're going to have a volume of our unknown, our total volume, and again times the concentration of our unknown that we'd have here. And if we go ahead and kind of clarify what that is, our Vx is the volume of the unknown solution, and our V total is the total volume of our solution that we'd have here. So we're just looking at dilution factor effectively of how our concentration is diluted. And then our C sub x is our unknown concentration, which is typically what we're going to be trying to find. Now that's going to be divided by the total concentration of all the analyte that we'd have in there for our standard addition. And we're just looking at the ratio of our signals equals the ratio of our concentrations. And so again, we're going to have some concentration of X. So we're thinking of it being diluted because we've added a standard amount to it. And then we add a known amount of the analyte that we're looking at. And that's going to be the standard volume, again, divided by total, because this is all in the same solution, times the concentration of the standard that we took. So if we have a 1 molar stock solution and we took 5 milliliters of it and diluted it to 100, now we have a 0.05 molarity concentration. We're just thinking about the dilution that occurs here when we have that, and that would be the volume of our standard solution used. And then our concentration, C sub S, is the concentration of our standard solution. And now this takes into consideration how our signal is enhanced and how that relates back to our concentration that we'd have of our unknown. The third one here is going to be our internal standard. Our internal standard, we're again adding a known amount of the analyte and a standard together, collecting the data, and then comparing that to unknown samples. And so what we'll see here is that we're going to look at a ratio of our signal to concentration between these two. And so we're going to say the signal of our unknown divided by the concentration of our unknown is equal to, I'm going to put this F here, which is going to be our response factor, times the signal of our standard divided by the concentration of our standard. And our standard is, again, our internal standard. This is a different substance, a different sample than what we'd look at with our analyte. Our analyte is going to be different. And so we have to first figure out what this response factor is. Okay, so our response factor is something that tells us the ratio between what kind of response do we get for our unknown relative to our standard. Do we get the same response between the signal and concentration? Do we see a signal of 5 for 1 molarity for both of them? Or do we get a higher signal for our internal standard, or a higher signal for our unknown for the same concentration? And that's what this response factor is telling us. It's telling us the relative signal to concentration ratio for our unknown and for our internal standard. So what we're doing is we're looking at what kind of ratios do we have. So the first solution that we made up here, this solution here, is in order for us to figure out what our response factor is. Once we know that, we can go ahead and collect the signals of those in our unknown solution, as well as the concentration that we know of our standard, and then we'll go ahead and be able to identify our unknown. So we see there's 3 different methods, and we think, why would we want to use these? We would want to consider, like, what are the pros and cons of using each of these? And so first, the pros of thinking of using a kind of standard, normal kind of external standards that we'd see here. Some of the pros here is these are kind of more simple and straightforward. In addition to that, they're easy, they're quick, and what we can do is we can collect data on multiple samples quickly. Because once we have a calibration curve set up, I can have 700 samples and I can collect the signal for those 700 samples and collect the concentration from that. So it's pretty more straightforward to do when we're looking at these here. Then when we consider the pros for our standard addition, we went ahead and, ran out of room here. The pros for our standard addition here is that this can account for what we would classify as the matrix effect. And the matrix effect is basically thinking about how might the components of the solution that contains our analyte influence the signal that we would see. It may be that they kind of decrease the signal, they could enhance the signal, it just depends on what we're looking at. But we see that there could be this effect, this matrix effect, that the solution components, it's not just water, maybe it's seawater, and all the ions present in the solution are going to influence the signal that we'd see here. And so we couldn't necessarily just use external standards. We want to think about, I'm already adding the standard into the matrix, the solution that contains everything, and looking at how my signal is enhanced with that. So it's able to remove kind of that issue that we'd see. That's what's really important to think about when we'd use standard addition. Our last one here is internal standards. Why would we want to go through all this extra work of adding in something different? And what we'll see here, the main pro here that we would notice when we're looking at these is thinking about the fact that it can go ahead and remove any error from instrument inconsistencies. So if I have an instrument that is not really good at being really precise from one run to the next, to the next, to the next, perhaps there's some slight deviation if we're thinking about maybe gas chromatography, maybe our pressure or flow is not kept perfect, and we get these issues in area that are influenced not just by the concentration, and this is going to account for that. And be able to think of, I'm going to be able to compare if I have an enhanced area for maybe my internal standard, the standard that I add in relative to my original sample, all we can see is going to account for that. And so we see these two extra ones, the standard addition internal standards, are accounting for specific errors or issues that can happen when we're looking at different types of standardization. Now we think of what are the cons. The cons for external standards is that they cannot account for, one, any kind of matrix effect, and two, any kind of inconsistencies of the instrument. And so it becomes a problem with us with that if we're trying to use those, and we see here that that's where we'd want to use those other two. Now the standard addition again cannot account for instrument issues, and we think of this could just be extra work if there is no matrix effect. Because that's really why I would want to use standard addition. And so we see here, it just requires extra that every single sample that we have, if I have 500 samples, every single sample I need to add in a standard and then measure the unknown that we'll see there. And then our con for our internal standards is it's kind of unnecessary with an instrument that is very repeatable. So I don't need to collect multiple samples that we'd see here, and thinking of it's not going to change over time. It's very stable that we'd see here, and it wouldn't necessarily be required to do something like that. And so we can see there's specific circumstances when those are going to be used. And so if we kind of summarize this in thinking of when are the best opportunities for us to use these different methods. So the first one, when we're thinking about external standards, this is best when, one, there's no matrix effect for our signal of the analyte. So typically that would mean there is a simple matrix solution that we'd have here. So it's not really complex. I cannot replicate that in a external standard. Or number two, we have a very stable instrument. So we don't need to use these others too. So let me think about these other ones. When would we want to use standard addition? When there is a complex matrix solution. So we can't replicate it, like seawater. Seawater is really hard to replicate because if I collect it maybe by an inlet or not by an inlet, and we see it's very, very difficult to replicate something like that. or blood. Blood is a very complex matrix. You can't necessarily replicate that. These things that we are very complex, we would want to use standard addition because this is going to account for our matrix effect that we might see. Then our third one there is thinking of when would we want to use internal standards. We'd want to use internal standards when we have an unstable instrument. And this would be something that could be influenced by things that we cannot control perfectly. Like I mentioned, an example would be a gas chromatograph instrument, a GC. We see that it could have some inconsistencies as we go from run from pressure or flow that we'd see here when we're looking at that. So this summarizes these three. We're going to go ahead and look at how do we actually quantify these with some applications during our class time.